We were discussing strains in the last class. We just gave the flavor of strain, what strain is and how different kinds of strain act. So we discussed about normal strain, which acts, which makes sure that the element is elongated or compressed. And we also talked about shear strain, where we said that that there will be angular change in the material axis, in the sense if you take two lines which are perpendicular to each other, they will not remain perpendicular after deformation. So that's called shear strain. Today we are going to discuss how to calculate these strains. For material, we can talk about two things: average strain and point strain. Okay. So let's look at 1D. 1D. When we look at 1D, you have, let's say I have a bar here. Okay. And the bar has 2 points, P and Q. All right. And these 2 points in the bar are a little bit apart, and the distance between them is given by delta x. So the distance between P and Q is delta x. Okay. And now the material, the bar is given an axial force F. Okay. Which is equal to sigma into A. You know that already. We have solved many times. Now, when you give a extensional force, an elongation, tensile force on the bar, obviously the bar will elongate, right? Bar will move, right? So point P has moved to point P dash, and point Q has moved to point Q dash. All right. Then the movement of point P to P dash is given by U. Okay, and from Q to Q dash will be given by some other variable called U plus del U. Do you think that they will be equal? From P to P dash and Q to Q dash, do you think they will be equal? Equal to U, and Q to Q dash is equal to U plus del U. Okay, why is this? Because X is not same at P and Q. The coordinate of P and Q are not same, and therefore, since it's an elastic material, if P has moved by a distance, Q will not move by the same distance. It can move by an extra distance, right? For example, why is this right? Because this free end will have the highest extension, whereas this fixed end will have zero extension. That's why it is fixed, right? So the extension has varied from maximum here to zero here. So the extension is not same at all points in the bar. Each one of them will have a different value of extension. So from P to P dash, we represent it with an U. Okay, let's say that movement is U, whereas P Q to Q dash is given by U plus del U. Why U plus del U? Because Q will have a rigid body movement because of movement of P, and then it will have an extra movement because of its own position, right? So therefore, it will move how much P has moved, plus it will move some extra. That extra is del U. Okay, then the average strain in this case is, let us write its average is equal to delta U by delta X, right? Change in length by original length. Okay. By original length, original undeformed length, right? That's the definition of strain we learned in the last class. Okay, so this is my average strain in 1D. All right, is that clear? Any question on this? So change in length is given by this one. This is change in length, and this is my original length. So if you divide that, you get your average strain. Now, if you want to calculate point strain, we'll talk about point strain a little later. Okay. So this is called average strain. So it's clear. I suppose it is clear to all of you that the movement of P is given by U, whereas the movement of Q is given by U plus del U. Okay. U is function of X. U is function of X, the coordinate. Okay. And how is del U given? del u, if you know the first order rate of movement, rate of change, then du by dx into delta x is your del u. If I know the rate, what is the rate of change, of this extension? What is the rate of this extension per unit x, in the sense along the space? What is the rate of extension? If it's linear, then it's fine. It's one thing is okay. If it's linear, then first order is okay. So I can write it as that at every x, the extension is del u by del x. Therefore, for del x distance, the extension is del u by del x into del x, right? And this del x, this whole thing will make that this is your del u, the total calculation of the del u. So we'll come to that. Now let's look at point strain for a different, for 2D kind of orientation if you have in a material. So again, this is my xy coordinate and the z coordinate is going out of the plane. This is the geometry of the structure in an undeformed space, before the loading applied. And after the loading applied, it has, deformed a little bit. Some way it has changed its geometry, its shape, as well as its length. Okay. Now we consider 2 points in the original undeformed case, point P and Q, which are ds distant apart. Remember that they are ds distance apart, not x, ds. Okay, ds distant apart, P and Q. Now, when you deform them, and you can join them with a straight line, when it deforms, the P goes to P dash and Q goes to Q dash. They have their own new special positions, P dash and Q dash. And the line between them need not necessarily be straight line. It can be a curved line. Okay, need not necessarily be a straight line. It will be a curved line after deformation. It can be a curved line after deformation. Now, this was my coordinate system P. Okay, P is the coordinate system before deformation, which was given by x1, y1, and z. Because z is not changing, I'm not giving 1 here. Okay, and Q was the other point before deformation, and its coordinate is given by x2, y2, and z. So P and Q before deformation is known. This is before deformation. Okay, after deformation, what happens is it has moved to P dash and Q dash. Okay, now P dash I can write like before. Like before I have written that this has moved by u. Okay, so now the position of P dash is, it was initially x, so it will be x plus u, right? If it's initially x, it will be x plus u. So I can write them here also, that let's say this is initially x1. So coordinates of P dash of P is x1, coordinates of P dash is x1 plus u, right? Similarly, I can write coordinates of Q is x2, let's say, which will be equal to x1 plus delta x, and coordinates of Q dash will be equal to x2 plus u plus del u, right? Which will be written as x1 plus del x plus u plus del u, right? I can write these things. Okay, just I'm giving you a minute to look into it, ponder over it. I'll tell again, coordinate of P is x1. I just defined that. My Q in my original configuration was dx distance apart from P. So coordinate of Q is going to be x1 plus delta x, right? Which I can name it as x2, not a problem. X1 plus delta x. Now coordinate of P dash is going to be, it has moved by u after deformation, so it is going to be x1 plus u. So it is x1 plus u. So coordinate of Q dash is going to be x1 plus u plus del u, right? Because Q has moved by, sorry, x2 plus u plus del u, because Q has moved by u plus del u from its previous position. So the coordinates of Q dash is x2 plus u plus del u. Now x2 is x1 plus del x, so it comes out to be x1 plus del x plus u plus del u. Okay, that's the coordinates of P dash and Q dash. So similarly here also, we can look into coordinates of P dash and Q dash. Now look at here that it's not one-dimensional body, it's a two-dimensional body. So coordinates of P is given by both X and Y, and coordinates of Q is also given by both X and Y. And therefore P dash will have changes along X direction as well as changes along Y direction. Similarly, Q will also have changes along X direction as well as along Y direction, right? So P was X1, Y1, and Z. P dash will be X1 plus U1, Y1 plus V1, comma Z. Okay. So the coordinates of P dash is away from P by U1 along X and V1 along Y direction. Okay, it's a new coordinate. Remember that Y was not there in the previous because it's a 1D problem. It was only along X. Okay, so only along X, and that's why there was no Y coordinate system into it. But here now it's a function of both X and Y, and therefore I need to have extension along X, that is U1, and extension along Y, that is V1. Okay. Similarly, Q dash will be X2. Let's say its position is X2, Y2, right? X2 and Y2. So it will be X2 plus U2 and Y2 plus V2. Right? So U1, V1 here and U2, V2 there. I don't know the relationship between U1 and V1 right now, but I have to find the relationship between U1 and V1 to find out what is the strain in the material. Now U and V, the general representation of U1 and V1, U and V is obviously going to be a function of X and Y coordinate system, right? Here, if you see U was function of X because it will be 0 here and it will be maximum at the boundary, right? 0 at the fixed boundary, the U, and maximum at the free boundary. So U was a function of X coordinate, right? Here in this case, then U should be function of both X and Y coordinate, and V also should be function of both X and Y coordinate. Okay. Therefore, U1 is based on point P, so it is along X, and V1 based on point P again, but along Y. The deformation calculated along X is U1. Deformation calculated along Y is U2. V1. Therefore, U2 will be as it was beforehand. Remember, where did I write it? Yes. U2 is going to be U1, like here we wrote it, right? U1 plus del U. Del U was given by del U by del X into del X, rate of change. So that's what I'm going to write it. So U2 is going to be how much P has moved, that is U1, plus it will have extra movement because of this line change. That will be du by dx into del X. So rate of change along X direction into the distance between them along X. So that is del X. Similarly, rate of change along Y into the distance along Y. Same for V2, rate of change along X into del X, rate of change along Y into del Y. That has to be added with how much P1 has moved in B direction. Okay, so that's how you calculate you relate the previous motions U1 and U2, U1 and V1 with respect to the Q configuration U2 and V2. Okay, now if I go one step further, this picture makes it more clear, the coordinate points, right? It makes it more clear. So if I have again a same, you are looking at a planar coordinate system and Z is out of plane, and you have this body, right? And the body has a small cube, small element inside, right? And the element is given by dx and dy, elemental dx and dy. And the point, the P point has P, you can write it as P, Q, R, and S, right? P, Q, R, and S, right? The coordinates of this P, Q, R, S is going to be, if I assume P to be X and Y, X, comma, Y, then Q is going to be X plus dx, comma, Y, right? Because they are in a straight line here, right? X plus dx, comma, Y. S is going to be X plus dx because it has moved from P along X direction as well as along Y direction, right? S has moved both directions, X direction and Y direction. So it is X plus dx, comma, Y plus dy, because this distance is dy, this distance is dx. For point R, it has not moved along X, but it has moved along Y. So it is going to be X, comma, Y plus dy. Just look at it, this picture. It's not difficult to grasp it. So undeformed configuration, the PQRS coordinate systems are given as in this picture. Okay. Now in deformed coordinate system, the P point will move to a P dash point. Q point will move to a Q dash point. Now this Q dash point, please note, this Q dash point, P dash Q dash is not going to remain horizontal. Q will have deformation along horizontal as well as along vertical axis, Y axis. Both X and Y axis it will move. Okay. So first look at P. So this is my P, which has moved to P dash. So P has moved along X by an amount U, and P has moved along Y by an amount V. Okay. So the P dash point is given by movement along X is U, movement along Y is V. So P dash, coordinate of P dash is going to be X plus U, comma Y plus V, right? Because P was XY. So its P dash is going to be X plus U and Y plus V. Clear? Now Q dash, it is moved along X. So it is going to be X plus U du by dx into dx, the coordinate of Q dash. Similarly, the coordinate of what is that? Coordinate of Q, the Y coordinate of Q is going to be Y plus V plus dv by dx into dx. Where is Y? This is my Y. Y plus V is here, plus how much change it has made along that direction, right? Okay, so this much is the rate of change of V along X into dx. Because V is the coordinate, V is the deformation, right? How much V is changing in the direction of X, right? So that much V will add up to its P dash position. So that becomes Y plus V plus dV by dx into dx. Please note this X, the derivatives. They are very important. Okay. Now let's go to, similarly, I can point for S dash and I can point for R dash. Okay, same formulation will apply and we'll have the coordinates of P, Q, R, S. Now, why do we need coordinates? Because these coordinates allow me to, if I subtract the coordinates, right, I can find the length, change in length. That's why I need the coordinates. And it's very important to find out coordinates and then use them to find the change in length. Okay, so I'll stop here. No, I'll not stop. It's difficult to stop here. Yeah, so we'll start calculating point strain now. Okay, so we saw, right? So the point strain, epsilon of P, this picture we have seen, right? Point strain, so the definition of this diagram is already known to us, is going to be del plus U minus U, but to change in length by length with a limit del x tends to 0. That means you're not looking at an average strain between P and Q, you're looking at the strain at point P itself. Okay, so we're looking at a point strain at P itself, not an average strain between P and Q. So when I say del U, so this one, del U by del x, I need 2 points P and Q, right? And I'm finding the strain between points P and Q. So this is an average strain between point P and Q. But when I'm putting the limit del x tends to 0, I'm making sure that point Q coincides with point P. Therefore, we're looking at strain at point P itself. So that becomes equal to then del U by del x differential. Okay. So the normal strain along X, so this is written as epsilon xx. So normal strain along X at point P is given by del U by del x given point P. Okay. Right. So this is the strain measure that we use most of the time in our analysis. Unless I say that it's an average strain, you don't need to find that. You have to find this, the point strain. Okay. So if I do the same thing for all three directions, I will get epsilon x's average is going to be del U by del x. Epsilon y by average is going to be del V by del y, because V is along y direction. Similarly, for del z, epsilon z, it is going to be del W by del z. So, so the movement along x direction, the deformation is given by U. Along y direction, the deformation is given by V. Along z direction, the deformation is given by omega. Okay. or w, whatever you want to say. Here it is w. Okay, so u is a function of xyz again, v is a function of xyz again, and w is also a function of xyz again. Now, if you want to find point strain from the average strain, I have to put them to a limit, and if I put them to a limit, I get these coordinate systems. Right now, you remember that these are partial derivatives because u is function of xyz, v is function of xyz, and w is also function of xyz. And therefore, I have to take partial derivative with respect to x, with respect to y, and with respect to z to find the point strain along x direction, point strain along y direction, and point strain along z direction. Okay. Now, if I have to extend it, so this is not necessarily will come here. So this is the picture we just were reading. Okay. Same picture just we read before. It's the same thing here, same coordinates, and you see the same picture here. So what happens is, let's say you have a point A here. The A is given by a movement of, this is the point A, small a, which has A has moved to point A, which is given by u comma v, coordinate system of A and B. And then B, which is here, is given by u plus del u by del x into del x, v plus del u by del v. This is what we have done in just few minutes before. Same thing, the coordinates. Similarly, C also you can find out. So this picture is much more elegant than the previous picture because you can calculate everything properly here. Okay. Now, how do you find strains? So now, if you see this picture, it has also moved in this direction and in that direction. So the perpendicular line, which was like this before, okay, the two perpendicular lines or the perpendicular sides AB and AC is no more perpendicular to each other. So that has moved to small ab and small ac, which makes an angle. And now, if you remember our definition from the previous class, that if there is a change in angle which is lesser than 90, that means the angle changed from 90 to lesser than 90, you get positive shear strain, right? So this is a positive shear strain. Now there are two angles here, alpha and an angle beta. So Archis, there are two angles now, alpha and beta. So total shear strain is alpha plus beta. Okay. So total gamma xy, total shear strain is given by pi by 2. That was its previous angle minus its changed angle, right? Which is angle CAB. So minus angle CAB, which is equal to alpha plus beta, right? So I have to find what is alpha and I have to find what is beta and add them up to find my total strain, shear strain. So we know it's not difficult. We know tan beta and tan alpha. What is going to be tan alpha? Tan alpha is this by this, right? This triangle will give you my tan alpha. So tan alpha is going to be this divided by this, right? So what is this? This is, we know already. We have done it before. It's I'll blow it off so that you can see it properly. Partial derivative of uy divided by x, because this is the x, right? So how much increment in y you are getting with respect to x, right, into dx, so total. So tan is going to be this whole thing divided by this length. Now this length also has changed because there's an extension there, right? So it is, initially it was dx up to this point it is dx, right? But then there's an extension of du by dx, dux is by du. So ux is extension along x direction, right? And uy is extension along y direction. So how much extension along x direction is allowed per unit x multiplied by x? So that comes out to be tan alpha, right? So it's going to be dv by dx. V is this vertical distance, which is du by dx into dx, multiplied by dx into du by dx. So this whole length. If you do height by base, and then you assume that this is very small with respect to dx, so you bring dx out, you get 1 plus du by dx. So remember that we said for strains to be very small, it has to be much, much smaller than 1. When I say much, much smaller, it is really small. It goes into microns. Okay, it's 10 to the power of minus 6. You get strains in matters of 10 to the power minus 6, not even in near to 1. Okay, so that's very small. So if that is very small, I can easily, neglect that. And if I neglect that, I get dv by dx into dx divided by dx. All right, and that comes out to be something like this. Small strain alpha is du by dx. So it's also written y here. It's not y. We are representing them as v, right? So it will be u. We represent them as u. Okay, so this is v for us, and this is u for us, and that's v. Any uy will be v, ux will be u for us. Yeah, that's written. Yeah, that is written already. Okay. Yes, so this is again going to be v. Similarly, for tan beta, you can do the same thing and you'll get du by dy. So when you add them up, gamma xy is going to be dv by dx and du by dy. See the change in variables, change in v, so y-axis, change in the deformation along y-axis by x, and change in deformation along x by y. Okay, at point A. This is a shear stress on point A. So please have a look at it. I'll give you a minute here. So this is not, here it is not u, it's v, here it is not v, it is u, and here it is x, here it is y. So pay attention there. Okay. So this is how you find shear strain. So we found normal strain by the method of point strain along a direction, and then we extended it to all three directions, and we got du by dx, dv by dy, and dw by dz, del w by del z, right? Which for shear strain become little bit different, and it become del v by del x plus del u by del y. So we found shear stress on this one. I'll just hold on a minute here. As we discussed, is given by average gamma xy will be given by the average values like del v by del x and del y by del u by del y, not this is u. But when you do a limit of those, you will get the point strain, which is given by this formula here. Sorry. Okay. Now we'll come to state of strain. We have learned state of stress. We know that state of stress is given by state of stress at a point. We are now familiar with this already. Sigma is given by sigma xx, tau xy, sigma yy, right? So therefore, the strain, state of strain at a point will be given by epsilon xx, gamma xy, epsilon yy. Now, these two gamma xy is going to be same. They are again, this is also a symmetric matrix. Okay. And we know how to find epsilon xx, epsilon yy, and gamma xy. We just have done those things. So epsilon xx is going to be del u by del x, epsilon yy is going to be del v by del y, but gamma xy is going to be del v by del x plus del u by del y. The change in coordinates, we should note the change in coordinate here. Okay? Because that's important. You don't forget that. Don't mistake it. All right. So u is deformation along x direction and v is deformation along y direction. So you take the derivatives in the opposite sense, in the reverse sense. So this is called your state of strain in a 2D planar body. Right. Now, there are two things to understand. This is called engineering strain. Please note, this is called engineering strain. There is something else, tensorial strain, which we'll discuss now after this. So gamma xy is called engineering strain because engineers use it most of the time. And this is the formulation for a 3D strain. The same thing is extended for 3D. So epsilon xx is del u by del x, epsilon yu is del v by del y, epsilon del w by del z, del w is the deformation along z direction. So gamma xy will be given by this, gamma xz will be given by this, and so on and so forth. The strain matrix, so state of strain at a point in a 3D member is going to be given by epsilon xx, epsilon yy, and epsilon zz as diagonal limits. And off diagonals are with gamma, which are for shear stresses. So these are all shear strains. And this is called engineering strain. I'll tell in a minute why it's called engineering strain. And also note that the strain components, that gamma xy is going to be gamma yx because complementary shear stresses are equal. So complementary shear strains will also be equal. Same here and same here. Now, we write all of them in a very easy notation. That was engineering strain. Now we are looking at strain tensor. Okay, it's different from engineering strain. I write it as different from engineering strain. Okay, engineering strain is given by this. Please note there is gamma xy, which is du by gamma xy, which is du by dy, del u by del y, and del v by del x. Now in engineering strain, that becomes half of, in tensorial strain, it becomes half of del u by del x, del u by del y, del v by del x. Okay. The coordinate system has changed. Instead of u, v, and z, now I have x1, x2, and x3, which were earlier x, y, and z. Because this is a mathematical notation and it needs a mathematical orientation. So instead of writing u, v, and so I'll write that instead of writing x, y, and z, we write x1, x2, x3, and instead of writing u, v, and w, we write u1, u2. So same thing, but the variable naming has changed because now we are getting into tensorial matters, right? And the total strain, every strain, all the strains, all these 9 strains that we have, all these 9 strains that we have here can be represented by only one single equation. That is for linear, okay? This is linear. Remember this is not non-linear. Linear strain deformation. This is called strain deformation relationship because U1, U2, U3 are deformations. And what you're getting here is strain epsilon, right? So these are called strain deformation relationship. Okay. And this is how it is given. Just in a single note, you can write it in linear that half of del of u transpose plus del of u again. So you can write that in ij format, in tensorial format, is epsilon ij is given by half of ui comma j and uj comma I. See the change in notations, I comma j here and j comma I there. Okay. Now comma means derivative, partial derivative. Okay. So comma gives you partial derivative. Uij is the first indices represent the deformation direction and second represent the coordinate. So I goes from 1 to 3. So 1, 2, 1, 3. 1 coordinate to 2 coordinate to 3 coordinate. Similarly, j goes from u1, u2, and u3. So epsilon ij, since there are 3 notations, 1, 2, and 3, 1, 2, and 3, I will have epsilon 1, 1, epsilon 1, 2, epsilon 1, 3, again epsilon 2, 1, epsilon 2, 2, and epsilon 2, 3. Similarly, I will have epsilon 3, 1, epsilon 3, 2, and epsilon 3, 3. Okay, so these 9 components can be represented by a single variable called epsilon ij, where I moves from 1 to 3, j also moves from 1 and 2 and 3. Okay, so that's what it is here. And it is given by this one. So epsilon 1, 1, if I write it, is going to be half of u1, comma 1 plus u1, comma 1 again. So half of u1, comma 1 plus u1, comma 1 comes out to be u1, comma 1. What is u1, comma 1? I said comma means derivative. So it is u1 derivative by x1. So u1 is u and x1 is x. So it is du by dx. So you see, first strain variable is du by dx. That is all have been done here for you. Okay, I've written, so x1 is given by u, y, x2 is given by v, and x3 is given by w. That's what we discussed, right? So ui comma j is del u by del x j. So comma means partial derivative. So you see that del u I comma del x j. So you are not writing xj here, you are only writing j. So it's short notation. So for I equal to 1 and j equal to 1, it becomes u1 comma 1. So it becomes del u by del x because this one represent x1. Okay, x1 is x. If you want, I will write that also, x1. X. Similarly, you can go for u2 comma 1. So u2 comma is going to be partial derivative of u2 with respect to x1, first coordinate, right? So what is u2? u2 is the second directional deformation, which is going to be v. and this is going to be your x2, which is x1, which is your x again, since x1 equal to x. Similarly, you look at something else. Let's say we look at 2. ui comma 2, right? So u1 comma 2, I is 1 and 2 is 2. So u1 comma 2. So this becomes partial derivative of u1 with respect to coordinates in 2 directions. So it is going to be u1 by y. u1 is u, right here. u1 is u divided by y. Since x2 is y coordinate. Similarly, x3 is z coordinate. All right. Is that clear? I'll pause, resume. Now, if you find the strains, the strain has to be in this format. And I have derived for a few of them here. You can go through this and you will see that these are all done. So tensorial normal strain, engineering normal strain, they are equal. But for shear strain, they are not equal. There is a half relationship there. Okay. So you have to just pay attention there and do it. So please go through this part. I've explained the previous page, so this page should be easy for you to understand. Okay, you just have to plug these values from the previous page and you see that what happens here. So this is a relationship between engineering strain and tensorial strain. So epsilon xx remains epsilon xx, epsilon xy goes to gamma xy by 2. And also you need to pay, Akhil, you need to pay focus on whether I'm writing epsilon or not. If I'm writing epsilon xy, it means it's a tensorial strain, and if I'm writing gamma xy, it means it's an engineering strain. And don't worry about marks, because marks will not be deducted if it is different.
Okay, sir.
But you need to pay attention when you design things. You generally look at gamma xy, not at epsilon xy.
Yes, sir.
Apart from tensorial strain, apart from the normal whatever strains I've talked about, there is something called volumetric strain, which is change in volume of the body. Okay. So this is what is there. So change in volume of the body is final volume minus initial volume divided by initial volume, and that comes out to be epsilon xx plus epsilon yy plus epsilon zz. So addition of all the normal strains. Okay. Just for a definition, you have to remember this. What is a volumetric strain? There are a few points which I have written here. Please go through. What is the average versus point strain? What is the normal versus shear strain? Mechanical versus thermal strain. Thermal strain is very important. We'll do a few problems for thermal stress and strain. Finite versus infinite small strains. Okay, so finite strains are large strains where the relationship will be non-linear relationship. So this will not be valid there. This relationship will not be valid here. It will add it up with grad of u transpose grad of u. Okay. So that will be the second order that will come into play. So we are not going to do that in this course. So just written there. And strain measure. How do you measure strain? So generally strains are unitless, right? They don't have any unit. So I would write it. Why do I write it? Somewhere I have to write. Otherwise you will say that we have not written it. Okay, let me write it here. Strains has no unit. Okay, it is ratio of lengths. Okay, so it has no unit. Order of strain is mainly 10 to the power of minus 6. Okay, so sometimes we represent strain as 10, not write 10, let's say we write it as 26 micron, which means 26 into 10 to the power of minus 6 meter by meter. Okay. So generally they are in microns, right? So they are in 10 to the power minus 6 most of the time. So we don't write it every time that 26 into 10 to the power minus 6. We write it as 10 to the power of 26 micron, which means it's 10 to the power minus 6 meter by meter. So if we write 261 micron, which is equivalent to 261 into 10 to the power minus 6, is the value of the strain. Okay, that's how we represent strain. But strain has no unit, so don't write micron as the unit of strain. Micron is not a unit of strain. That only replaces that 10 to the minus 6. Like we in stresses, we write 26 MPa. When we write MPa, it means 26 into 10 to the power of 5 Pascal, 10 to the power of 6 Pascal, which is equal to 26 into 10 to the power of 6 Newton per meter square. Right. So these are the standard things, engineering standard things. Okay, that are not mathematical. They are the engineering standard things because it helps engineers. This is engineers' language. It helps one engineer to understand the language of another engineer. All right. So with that, I'll stop. Thank you very much.